Welcome back, let's resume. In the previous video clip, we talked about an example problem that you have to apply this formula over here. Formula number 2 of page 441. V equals the integral from a to b 2 pi x f of x dx. Now, this is the most elementary formula, but not the most general one. Far from it. It is too specific. It is about rotation, about y-axis, and then it is about region under curve y equals to f of x, which is positive, and the lower edge is always the x-axis. So we are talking about very specific situation, kind of like this, as you see in figure 3. Now, if you have curved edge both on the top and bottom, then you'll have to make appropriate adjustment to the height. And if the rotation is done by not y-axis but some other vertical line, further adjustment is going to be necessary. And we're going to talk about those in my Mathematica notebook I created, because it has a little bit better visualization than this textbook with animations and so on. But before that, let me show you this bundt cake kind of picture we already saw in my Mathematica notebook. Let's move on to a kind of example like this one, figure 8. In this case, height of the cylindrical shell will change because the top curve and bottom curve are, well, they're both curved, not the x-axis, so the height will be the difference of y-coordinate values. So we have to subtract one function from the other. There are other examples here, but the visualization is not that simple. So let's move on to my Mathematica notebook here. And let's initialize it. I think I have already done that, but it doesn't hurt to do it twice. And then, okay, here are the volume formulae. This is the most general one. And then, oh, excuse me, this is the most elementary one. This is the most general one. The radius is r of x, this radius of rotation, and height is given by h of x. Usually, height is given by the difference of two y-coordinate values, upper function minus lower function. So y2x minus y1x is h of x. That's often used too, but this is the most general one that I'd like to use. Here are some examples, and let's begin with the most elementary one. And here it is. We have y equals to e to the negative x squared and y equal to 0. So we have top curve and bottom line. Bottom is just x-axis. And then x equals to 0, x equals 1. Those are two vertical line segments. And then rotated about the y-axis, consequently generating this picture here. The left-hand side picture, this kind of thing. And it is drawn semi-transparently so that you can see the cylindrical shell forming like this. In the right-hand side half of the 2D picture you see on the right-hand side is the region we have. And then as we change the x-coordinate value from 0 to 1 and take a line segment and rotate it around, you're going to get a cylindrical shell as you see in the left-hand side picture. And the radius of that rotation is just the x-coordinate of this line segment. So what we have to use the first formula here, 2 pi x f of x dx. As a matter of fact, we don't have to. It's just that in this general formula, radius r is just x, and then height is just f of x. In any case, if you do that, then you're going to get this kind of computation. I decided to put 2 pi outside of this integral. That's the same. And then x f of x, and here it is, x times e to the negative x squared. How do you do this kind of integral? Excuse me. Okay. I momentarily lost the control of my mouse. Now, how do you do this kind of integral? You'll have to do some kind of substitution And if you open it, here it is, y equals negative x squared, dy equals negative 2x dx, and so on. No cheating. And I'm gonna ask you to do these kind of things on your own, and look up the answer key only when it is necessary. Here are Mathematicas computation. In the end, you'll have to have this kind of answer. Does it match? Yes, pi 1 minus 1 over e. Yes, that matches. Okay, let's go to another problem here. This time, let's go to problem B. This time, y equal to 3 plus 2x minus x squared. That's going to be parabola. X plus y equal to 3. That's going to be a line. So we expect something like this. Okay, excuse me, I don't know what happened, but momentarily I lost the control of my mouse again. Okay, I'm back, and here it is. So we have a parabola, y equal to 3x plus, 3 plus 2x minus x squared, the top parabola, and x plus y equal to 3, equivalently speaking, y equal to 3 minus x. Okay, so if you subtract one function from the other, you're gonna get the height. So upper function minus lower function, that's gonna be the height. And then rotation with respect to the y-axis, so we just use the first formula, 2 pi x, and height is f of x minus g of x dx, and calculate it. Well, this is going to be an elementary computation, so I'm going to leave the rest, the detail, to students. Upper function minus lower function, excuse me, 3 plus 2x minus x squared minus 3 minus x with parentheses, and integrate it, apply fundamental theorem. If you do it right, you're going to get 3 pi over 2. By the way, here's the visualization. So as you move from x equals to 0 to x equal to 3 in the right hand side 2D picture, you get a cylindrical shell forming in the left hand side. Fix anything, this line segment is okay. Take this line segment and rotate it with respect to y-axis, and then we get cylindrical shell like this. The radius of this rotation is the x-axis, so we have to have just 2 pi x. Now, what if the rotation is with respect to the x-axis, like this one? And then here's the visualization of the 3D curve. Okay, here it is. The same thing. Here is a visualization of the cylindrical shell, and as y-coordinate moves from 0 to 3, we have this horizontal line segment. And then take one and then rotate it around the x-axis. We have a cylindrical shell like this. As a matter of fact, if you think it's a little bit difficult to see it that way, all you have to do is to change the viewpoint. And then now, what do you see? We have the usual case. So we have the height and then the rotation and everything. So what is the moral of this story? All you have to do for this kind of problem is to exchange x and y. So y plus x is equal to 3. Not that it requires any change. Y equals 4 minus x minus 1 minus 1 squared. Y plus x is equal to 3, so this is y equals to negative x plus 3. That looks a little bit better. So we have a line, and then we have a parabola about the y-axis, and then this problem is exactly the same as the given problem, and we can use the same technique as before. So if you're confused, just exchange x and y. Now the final problem is a little bit more challenging because the rotation is with respect to a vertical line x equals negative 2, not the coordinate axis. And here we go. We have two parabolae, blue and red, and we are rotating it with respect to this vertical line, x equal to -2. Here's the visualization, and we can see in this animation how the cylindrical shell is forming and how it is sweeping through the solid. Now, the 3D figure in the left-hand side is cool, but it gives you too much information. The right-hand side picture, the 2D picture, is easier to deal with, to tell the truth. And given x coordinate value, you get this line segment here, and rotate it with respect to x minus 2, x equals to -2, this vertical line there. Now, what is the radius of this rotation? It's not just x, because x is this distance between this line segments between these parabola and then the y-axis. You have to go a little bit further, so it's not x but x plus 2. So radius r is x plus 2, and then you have this f minus g, upper minus lower function, and then integrated, we're gonna get this kind of computation. So 2 pi, this is the radius, and this is the height. Detailed computation is left to the students because that's just a elementary integral problem. Finally, let's answer the question why? Here it is. Let's begin with the volume element, and we have to find out on one individual cylindrical shell's volume, and then we are going to add them together. And in figure 2 of our textbook, it shows you one cylindrical shell. It is given by the difference between two cylinders, V2 given by, well, outer radius, outside, and V1, the inside. So hollow part is subtracted away, then we're going to get a volume of this, a single volume element. There's a bit of a problem here. We're talking about the difference, V2 minus V1, so left-hand side should have been delta V. Also, this big V, the capital V, is reserved for the volume of the entire solid, not for a single volume element, so I don't really like this notation here. Consequently, let's move on to my mathematical notebook here, and then let's go from here. By the way, we are trying to deduce this main formula there. Now, the volume element delta V is given by V2 minus V1, the same thing that I talked about before. Now, what is the volume formula of a cylinder? It's pi r squared h, but radius for V2 is r2, so r2 squared, and radius for V1 is r1, so we have r1 squared. Some algebraic manipulation, we take pi h outside, and what do you have left? R2 squared minus R1 squared. Now, let us factor this further. A squared minus B squared is A plus B times A minus B. So we can express it like this. R2 plus R1 times R2 minus R1. Now, pay particular attention here. R2 minus R1 is the difference. So it's delta R. And then when delta R is really small, R1 and R2 will become pretty much the same, so we can simply write them all as R, and then we have R plus R. Consequently, we get 2 pi HR delta R, as we see in the last line. That's individual volume element delta V. So if I add up all these delta V's, then we have a Riemann sum, and each delta V is this one, so we get this expression over here, 2 pi RH delta R. This is a Riemann sum. So if we take the limit, then delta R becomes dr, and these remain as integrand, and the sum will become an integral, minimum to maximum. And that generates the original formula here, 2 pi r of x times h of x dx, because radius is now changed into x. And that's how this volume formula is coming into play. And of course, we can use h of x is y2 minus y1 in some special cases.